Hello, it's time to get into Module 10, which deals with differences in means, and in this first part we will look at the case of known standard deviations. So far we've been discussing both confidence intervals and hypothesis tests for a single mean or a single proportion. But there are situations where we want to compare two populations. For example, we may want to compare the means of two populations, mu1 minus mu2. where mu1 is the mean of group 1 and mu2 is the mean of group 2. Again, we're going to have a choice of either doing a confidence interval or a hypothesis test on mu1 minus mu2. As I said, there were several situations or many situations where you may want to compare means. For example, a business might be interested in the average production rate at two different plant locations. Or a firm might be interested in an estimate of the difference in the average cost of labor at two different locations or in two different cities. So situations like that involve comparing the means of two populations. Now there's several methods for doing this depending on what we know or don't know. We're going to start with the first method, probably the easiest method. Let's assume you've taken sample sizes N1 and N2 from the two groups, and that both of those sample sizes are at least 30 for the central limit theorem to apply. You're going to take independent random samples from the two populations, and let's assume for right now that we know the population standard deviations of those two groups. Let's go back for just a moment. We're going to start with a confidence interval, but let's go back to the general idea to a confidence interval. Remember, most confidence intervals, or a lot of them, have the general format that we want a point estimate, and then we go plus or minus some margin of error. Recall when we estimated a single mean mu, our point estimate was x bar. So it shouldn't be that surprising that when we want to estimate a difference in two means, mu1 minus mu2, our point estimate is going to be x1 bar minus x2 bar, where x1 bar is the sample mean from the first group and x2 bar is the sample mean from the second group. It turns out in mathematics you can prove that x1 bar minus x2 bar is an unbiased estimator, and that its sampling distribution is approximately normal by the central limit theorem for sample sizes of 30 or more. You might also recall that when we form the margin of error for a confidence interval, we need the standard error of the estimate, or the standard deviation of the point estimator. So we need the standard deviation of x1 bar minus x2 bar. Now we're just going to give you the formula for it here. Sigma x1 bar minus x2 bar is the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Again, you don't have to worry about where that formula comes from in mathematics. It should look somewhat familiar if you remember from an earlier module, the standard deviation of x bar, remember when we had just a single mean, was equal to sigma over the square root of n. In this case, where we have two of everything, we have two standard deviations, we have two sample sizes, two sample means. This should look somewhat familiar given your experience with a single mean. Now we can put this all together into a confidence interval. And we will get the formula x1 bar minus x2 bar, which is our point estimator, plus or minus, we can use a z statistic here because the distribution is assumed to be normal, times the standard deviation that we just gave you. Again, this just reminds you of all the notation. N1 and N2 are sample sizes from the two populations. By the way, it doesn't matter which group you call group 1 and which you call group 2, as long as you keep it consistent throughout the problem. Sigma 1 and sigma 2 are the population standard deviations. Notice in this formula you're going to have to square them, which makes them become the variances. Always be a little bit careful with that because some problems will give you the standard deviation, some will give you the variances. x1 bar and x2 bar, as we've already discussed, are the sample means that you get from your two samples from populations 1 and 2. And as always, z alpha 2 refers to the z value for a 1 minus alpha level of confidence. which would leave a probability of alpha over 2 in the end or the tail of the distribution. Let's do an example. A student, as part of a statistics project, decides to compare the prices of gas at 2 locations, let's say Chicago and Hammond. She takes a random sample of 40 Chicago gas stations and 50 Hammond gas stations. Assume the population standard deviation of gas prices is 10 cents, which in decimals will be 0.10 in Chicago and 0.07 in Hammond. In the Chicago stations, the student got a sample mean price of $2.25 a gallon, and in the Hammond stations, they got a sample mean of $2.05 a gallon. Calculate a 95% confidence interval for the difference in the mean prices between the 2 locations. Okay, we're going to let Chicago be group 1 and Hammond group 2. And if we simply take all the numbers from the problem and plug them into our formula now, x1 bar is 225, x2 bar is 205. We know the z-value for 95% confidence is 1.96 times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. If you work that all out, you will get the two ends of your confidence interval to be 0.16344 and 0.23656. And again, sometimes we write our final confidence interval in the following way. You're hoping that the true difference in mean prices is in this interval. Translating this from decimals into cents, into dollars, we estimate the population mean gas price in Chicago is between 16.344 cents and 23.656 cents higher than it was in Hammond. Notice that both of those endpoints are positive values, which implies that mu1 is greater than mu2. If mu1 is greater than mu2, then of course mu1 exceeds mu2, and that will generally be indicated when you get positive values for both of your endpoints here. You can do this confidence interval on a TI 83 or 84. Press the Stat button, scroll over to Tests, scroll down till you find one that says 2-sample Z interval. On my calculator, that happens to be number 9. Press Enter. On a problem like what we just did, where the statistics have been given to you, choose Stats. If you were putting in the raw data into lists, you would choose Data. The calculator will then prompt you to give it the standard deviations of the two groups, sigma 1 and sigma 2, as well as the sample mean from the first group, the sample size from the first group, the sample mean from the second group, and the sample size from the second group. Finally, you enter the level of confidence, 0.95, and then press Calculate. And you should get very close to the confidence interval that we gave you a minute ago. The only difference would be for rounding. Okay, that's how you form a confidence interval for a difference in means, assuming known population standard deviations. You could also test a hypothesis for mu1 minus mu2. We can take what we've already learned and convert it into a hypothesis test. We're going to let D0 represent the hypothesized difference in the two means. In other words, D0 is basically equal to mu1 minus mu2. The most common value for D0 in a hypothesis test is going to be 0 itself. Because if D0 is 0, that means the two means are equal. If you had 0 equals mu1 minus mu2, that means that mu1 must be equal to mu2. We'll look at that more on the next slide, I believe. As always, you have three choices or three possibilities for a hypothesis test. You can have a one-sided right-tail test, where the alternative is going to say that mu1 minus mu2 exceeds the value of d0 in the null hypothesis, which again is usually 0. You can have a one-sided left-tail test, where the alternative says mu1 minus mu2 is less than d0, or you can have a two-sided test, where the alternative says mu1 minus mu2 is not equal to d0. Again, as always, we need the equality part in the null hypothesis. It can be a less than or equal, or a greater than or equal, or just an equal to. Again, you learn which form of the hypothesis to use by how the problem is worded. As I was saying a minute ago, the most common value for d0 is 0, in which case you're basically hypothesizing that the two means are equal. And as I pointed out a minute ago, we always need that equal portion in the null hypothesis, where the alternative can be a greater than, less than, or not equal to. Now we're going to need a test statistic to test any hypothesis. And actually, again, if you go back to what we did for a single mean back in Module 9, I believe it was, the formula should look fairly similar to you in some ways. Our test statistic here is going to be a z-statistic, because we're assuming known standard deviations and large enough sample sizes for the distribution of x1 bar minus x2 bar to be normal. We're going to take the difference in our sample means, x1 bar minus x2 bar, subtract the hypothesized value of d0, which again usually just drops out of the formula because it's normally 0, and divide by the standard deviation. Again, if you were going to go back to Module 9 and look at the formula for testing a hypothesis about a single mean, you'll see a lot of similarity there. When we did a single mean, you took the sample mean minus the hypothesized value divided by the standard deviation, sigma over the square root of n. Well, now we just have two of everything, so the formula looks a little different, but it's the same general idea. Our best estimator, subtract the hypothesized difference over the standard deviation. If you're using the critical value approach, then if it's a right-tailed test, you're going to reject in the right end of the standard normal distribution. If we get a z-value above z alpha, which means, again, the z-value that leaves an alpha probability above it. If it's a left-tailed test, you're going to reject in the left end of the distribution. If you get a z-value below negative z alpha. And if it's a two-sided test, you're going to reject in both ends of the distribution. You cut alpha in half. You'll reject if you get a z-value above z alpha over 2 or below negative z alpha over 2. Let's use the same problem that we did for confidence intervals. Let's go back to our gas prices in Hammond and Chicago. Suppose we want to test at the 1% level of significance that the average price of gas in Chicago, which was group 1, is greater than in Hammond. Notice if we want to test is the average gas price in Chicago greater than Hammond, that would mean that mu1 minus mu2, average gas price in Chicago minus average gas price in Hammond, that difference would be greater than 0. If a difference is greater than 0, it tells you that the first item is greater than the second one. We usually write our hypothesis test here on differences. The null will be that there is no difference, or we could say less than or equal to. Again, the less than is not the important part of this null hypothesis, it's the equals part that we're mainly interested in. If mu1 minus mu2 equals 0, it would say the two means are equal. We choose a level of significance. Let's let alpha be 1%. We then have to calculate our test statistic. Take the difference in your sample means, subtract the hypothesized difference of 0, and divide by the standard error of the differences. Again, be careful with the mathematics. Be careful plugging the numbers into your calculator. Lots of calculation errors that can occur here. But you should get a test statistic of 10.72. Again, remember, we can do either the critical value or the p-value approach, and we're going to demonstrate both. If you're using the critical value approach with a 1% alpha level, your critical z-value is 2.33, and we'll look at that graphically in a minute. So we would reject the null hypothesis if our test statistic exceeded 2.33. Well, in this case, it certainly does. 10.72 that we just calculated exceeds 2.33, so we reject the null. By rejecting the null, we're concluding what's in the alternative, which basically says the average price of gas in Chicago is greater than that in Hammond. And here's kind of a graphical look at the critical value approach. Our critical value was 2.33. That's the z-value that leaves a 1% probability above it. So we decided to reject the null if we get a z-value above that point. And 10.72 is probably well out into the end of our tail of our z-distribution. And therefore we reject the null hypothesis. Alternatively, let's do the p-value approach. Recall with the p-value approach that you always reject the null hypothesis if you get a p-value less than or equal to alpha. So in this case, with alpha equal 1%, 0.01, we will reject if we get a p-value less than that. Remember how to find the p-value. You take your calculated z-value, in this case 10.72, and since this was a right-sided test, you're going to find all probability to the right of that. Well, 10.72 goes way off your z-table because there's almost no probability left beyond 10.72, so we'll just say it's approximately 0. Wavy lines meaning approximately. So our p-value is clearly less than 0.01, so again, we get the same decision. We reject the null hypothesis, and again, we conclude that average gas prices in Chicago exceed that in Hammond. Looking at the p-value, remember with the p-value, we're going to compare two probabilities rather than comparing two z-values. One of those probabilities is the alpha level, which was here 1%. The other is the p-value, which we just calculated to be very close to 0. And if the p-value is smaller than alpha, that tells you that you're out in the rejection region. Again, you can do a hypothesis test on your calculator. Remember again that a hypothesis test on the calculator will only give you limited information. It doesn't tell you how to write the hypotheses or how to state your decision and conclusion. Again, press the Stat button, scroll over to Tests, go down to number 3 on my calculator, which is probably number 3 on yours, which says 2 sampled z-test. Press Enter. Again, if the problem gave you the means and standard deviations, as we just did on our problem, choose Stats. Input all of the data you were given. Population standard deviation for group 1, for group 2, sample mean for group 1, sample size for group 1, and the same for group 2. Put in the form of your test. Is it a two-sided or one-sided test? And if it's one-sided, what does the alternative hypothesis say? In this case, we were testing is mu1 greater than mu2, which would mean that the difference is greater than 0, so choose the greater than mu2. Put in, and then you simply hit the calculate button. The calculator will give you the z-value that we had, 10.72. It'll give you the p-value, which is very tiny. In fact, it's given to you in scientific notation, very small p-value. And from the p-value, you could perform the test in that manner. Okay, that is the end of the first part of this module.